we start talking about the nervous system and its inner workings, we have to talk about something more fundamental: electricity. We need to go back in time to the 18th century in Bologna, Italy. Luigi Galvani was a well-known physician, physicist, and philosopher residing there. Back then, you could be a physician, physicist, and philosopher all at the same time. In 1771, he was dissecting a frog when his assistant touched a nerve in the frog's leg with a metal scalpel that had picked up an static charge. The frog's leg moved. The apparent reanimation of the frog was extraordinary and unprecedented. Galvani thought that he had discovered the key to life, an inherent electricity within animals which led to movement. He even posited the existence of an animal electric fluid that gave rise to the effect. Alessandro Volta, a physicist and contemporary of Galvani, repeated Galvani's experiments, but doubted the existence of an electric fluid intrinsic to animals. Spurred on by Galvani's theories, Volta eventually went on to develop the first battery, proving that similar electricity could be generated outside of a living creature. Galvani, like so many historical figures, died depressed and impoverished, a victim of cruel political fate. But his name lives on. Volta, Galvani's rival, coined the term galvanism to refer to electrical phenomena in living creatures, and Galvani's name appears as the root of many modern terms, such as galvanic and galvanometer. Taken together, Galvani and Volta's work was immensely important, and their discoveries ignited the study of electrochemistry and bioelectricity. While Galvani's notion of intrinsic animal electricity wasn't 100% on target, he was on to something. Bioelectricity plays a central role in the function of the nervous system. We're going to spend the next few sections exploring these electrical properties in an individual cell in the nervous system, working from small to big, simple to complex. Although there are many different kinds of neurons, the same basic electric principles underlie their function. We'll start by looking at the electrical principles that come into play when the cell is at rest. If we look at a typical neuron, you can see that it has a variety of parts. A cell body, or soma, that houses the cell's nucleus and a variety of cellular machinery. Extending out from the cell body are fine processes called axons and dendrites. The outer surface of all of these parts is made up of a bilayer of lipid molecules that partition the inside of the cell from the outside. This is called the cell membrane. We'll be spending a good deal of time talking about each of these various parts of the neuron, but for now, let's just concern ourselves with a small patch of membrane somewhere on the soma. There's an awful lot of important stuff going on in this humble little patch of membrane. Even when the cell is at rest, it's not electrically neutral. If you measure the voltage, the difference in electrical potential energy across this membrane between the inside and the outside of a living neuron, you'll see a small but important voltage called the membrane potential. You might be familiar with the idea of potential energy or stored energy. A battery, for instance, generates an electrical potential or voltage between its positive and negative terminals. When we hook up a wire across the terminals, this electrical potential causes electrons to flow through the wire from the negative terminal to the positive one. We can use this flow of electrons to do work, such as lighting this light bulb. If we measure the potential difference between the inside and outside of a neuron at rest, we measure a voltage of about negative 70 millivolts. Voltage is a relative quantity. We can only really meaningfully talk about the voltage between 2 points. When we say that the voltage at a particular point in a circuit is a certain number of millivolts, we must also define what point we're calling zero. By convention, neurophysiologists consider the outside of the cell to be this reference, which in electrical nomenclature is called the ground. Voltages inside the cell are measured with respect to this extracellular ground. To give you some perspective, a AA battery has an electrical potential of 1.5 volts. So this resting potential in the cell at negative 70 millivolts is about 20 times smaller in magnitude. So the neuron has a small but not insignificant voltage across the cell membrane. How did it get this way? Well, first, let's state what it's not. It's not a battery like the AA we showed you earlier. Batteries like that generate voltages through chemistry, electrochemical reactions that release electrons on one side and that use up electrons on the other side of the battery. The key to understanding how neurons generate a resting potential lies in the stuff on either side of that humble cell membrane. Both the inside and outside of the cell are basically made up of water with a host of stuff: proteins, ions, and sugars. There are a whole host of charged ions and molecules floating in and around the cell, including magnesium, bicarbonate, phosphate, sulfate, and many proteins. We'll be focusing for now on just a few key players: the charged ions sodium, potassium, calcium, and chloride, which are present in reasonably high concentrations and are important in generating a resting potential in the neuron. If we want to understand the resting potential, we need to first introduce two basic phenomena in nature: diffusion and electrostatics. Diffusion is a process by which particles spread out or mix, for instance in a solution. Here I'll take a bit of dye and a beaker filled with water. I drop a bit of dye into the beaker and I wait. After the initial splash of the dye falling into the water, the dye spreads out very gradually, over the course of hours, until it's uniformly distributed in the water. This gradual spreading is diffusion. The movement of the dye is governed by the thermal movement of individual dye molecules. They're basically jiggling at an atomic scale and bumping into each other. The result is a sort of drunken random walk of any given particle through the solution. In the aggregate, the process of diffusion causes particles to move from regions of high concentration to regions where the concentration is lower. Even though it's a purely random process, for all intents and purposes, we can think of diffusion as an inexorable force driving particles down a concentration gradient, from high to low. This process turns up all over biology, and it's essential to life as we know it. The second key to understanding the resting potential is electrostatic force. We already alluded to these forces when we were talking about batteries. Let's dig a bit deeper into what's going on. Particles can have a charge associated with them, positive or negative. These charges serve as the basis of all electricity. Positive and negative charges attract one another, and like charges, positive and positive, or negative and negative, repel. Here's a basic schematic membrane. We can see the intracellular part of the neuron here, and the extracellular part of the neuron here. Our voltmeter has a ground electrode outside the cell, and the other end is in the intracellular part of the neuron, measuring the difference in voltage between these 2 points. Suppose that we put an excess of negative ions on the inside of the cell, such that there's a potential difference of 60 millivolts across the membrane. Because we're referencing our measurement to the point outside the cell, we would say that there's a membrane potential of negative 60 millivolts. At rest, most cells in the human body actually have a negative membrane potential like this, ranging from negative 5 to negative 100 millivolts. In neurons, this resting potential is generally from negative 40 to negative 90 millivolts. How does this happen? That's what we're going to explore in this segment. Our aim is to leave you with an intuition for how concentration gradients and electrostatic forces can drive ion flows across the membrane. Each side of the membrane is basically electroneutral. This means that on each side, there's basically no net charge. This is because in the bulk solution, for every positive charge, there's a negative charge to balance it out. For clarity, from this point forward, we're not going to show this ambient soup of positive and negative charges, but it'll always be there. However, the membrane potential comes from a tiny imbalance that accumulates very close to the membrane. This charge imbalance generates an electric field across the membrane, which results in an electrical potential. If you've taken physics or electronics courses in the past, you may recognize that this arrangement is basically a capacitor. If you haven't heard this term before, don't worry. We'll be explaining capacitors in greater depth in a little while. Let's try to understand how and why this charge imbalance develops. We'll start with a simple example, and then build up to a more realistic membrane. The membrane you see here is a lipid bilayer with no openings, so ions can't pass through it. We'll talk about openings in the membrane, called ion channels, in a moment. Let's get rid of these for now. There are a whole host of positively and negatively charged species in solution on both sides of the membrane. Right now, let's just have an equal concentration of potassium on both sides. If we measure the voltage across this impermeable membrane, what will we see on our voltmeter? moving positive charges out of the cell in the form of potassium ions. Remember, we were electroneutral to start, with a negative ion to match every positive ion on both sides of the membrane. When you take away positive ions from the inside, you're left with an excess of negative ones. Meanwhile, the previously electroneutral solution on the outside has gained positive charges from the potassium, so it now has an excess of positive charge. This means that the inside will be more negative relative to the outside. And since the convention is to define the extracellular voltage as our zero reference point, the membrane potential would be negative. The excess charge doesn't just float around in the bulk solution, however. The laws of physics tell us that these extra charges will move to the membrane. In our example, the excess positive charges would line up on the outside of the membrane, and the negative charges would line up along the inside. Okay, so now we've opened up holes in the cell the potassium can diffuse through, and an electrical potential has developed. What do you think will happen to the intra and extracellular concentrations of potassium if we allow the system to go until it reaches equilibrium? A small amount diffuses through, but the concentration is still greater inside. This is because we're dealing with charged ions. If we just had uncharged particles flowing through, they would diffuse to the same concentration on both sides of the membrane. The reason that this doesn't happen for potassium is that we have an additional force to think about: electrostatic force. As we start moving more potassium down the concentration gradient from inside to outside, that additional net positive charge creates an electrostatic force that repels additional positive charges from diffusing out. But all forces aren't created equal. Let's get an intuition for what it actually takes to create a membrane potential of negative 80 millivolts, which is the equilibrium potential for potassium. What fraction of ions do you think we would need to move across the membrane in order for this potential to form? Don't worry, we haven't told you how to compute this number. Just take a guess. Moving just 1 in 100,000 ions across the membrane is sufficient to create a negative 80 millivolt membrane potential. The derivation of this number is outside of the scope of this course, but for those of you with a physics background, we get it from the equation for the relationship between charge and voltage in a capacitor. What does 1 in 100,000 ions actually look like? Let's take a look. This is what 1 in 500 ions looks like. You can zoom out and change the number of particles we're looking at in any given field of view. Great. That's our original ion in the middle, surrounded by a sea of particles. In biology, we're constantly confronted with very small and very large numbers like this, so it's helpful every now and then to take a step back and try to conceptualize what these numbers mean. In real cells and neurons, there are trillions of ions inside the cell, so even just moving 1 in 100,000 ions still means that we're moving millions of ions outside in order to create this equilibrium. The key thing to understand is that the electrostatic force for moving just a tiny fraction of charged particles to the other side of the membrane is enough to balance out the diffusion of a large number of particles. This gives you a sense of how much stronger the electrostatic force is compared to diffusion. Moreover, this means that even though ions do move across the membrane to generate membrane potentials, so few ions need to move that the concentrations inside and outside are effectively unchanged. Only a tiny proportion of ions move relative to the total number of ions inside and outside the cell. We can thus basically ignore the ions that move across the membrane when we talk about the intracellular and extracellular concentrations. Okay, So now we've established that there are positive potassium ions that leave the cell. Let's do a quick thought experiment. What if we magically added some additional negative ions to the outside of the cell to balance out those extra positive charges that came through the membrane? What would happen?